Okay, let's start. Hello, everyone. Today we have the third talk of our Trans-Pacific Colloquium series. Today I'm happy to present Vedika Khemani, who is assistant professor at the Stanford University and one of the leaders in the many-body localization. It's novel, very interesting, and actually for me it's quite surprising topic that has extended and pushed the boundaries of textbook thermodynamics. So Vedika has made her PhD in Princeton in 2016, and after a postdoctoral position at the Harvard, became a faculty at the Stanford University. She has got a number of fellowships and awards. I will mention only a few of them, including Early Career Award from the Department of Energy, and George Valley Prize from the American Physical Society, and fellowship from Alfred Sloan Foundation. It's actually very impressive. And before we start, I would like to make a short announcement. So as usual, questions are very welcome during the talk with help of this chat window in Zoom. And also it would be very helpful if you also write the number of slides that you're referring to. However, this time we won't interrupt the speaker, and Vedika will make a stop in the middle of a talk for questions, and you also will have a opportunity to ask questions at the end of the talk. Okay, so Vedika, please free to start, and we will enjoy the talk.
Okay, yeah, thank you very much for the Dimitri for inviting me and for this nice introduction. While I wish I was in Australia giving this talk, this is obviously the next best thing. Actually, I was just looking at the news yesterday and I saw that Qantas airline sold out a flight to nowhere in 10 minutes. So I think even those of you who are in Australia wish you were on a flight to Australia, but okay. So the subject of today's talk will be many-body physics in the era of noisy quantum simulators, okay? And specifically, I'll be telling you about one proposal to use such simulators for realizing a time crystal phase, okay? So this is work that we recently posted on the archive a couple of months ago. This is done in collaboration with a few people, but it was really led by my postdoc, Matteo Ippoliti, who's a postdoctoral fellow at Stanford. And the other people involved were Kostya Kajetsi, he's a researcher at Google, Roderick Mosner at the Max Planck Institute in Dresden, and Shivaji Sondhi at Princeton. Okay, so in recent years, something that's becoming increasingly clear is that we're witnessing this historic confluence of all of these different subfields of physics, ranging from condensed matter to AMO to quantum gravity, all coming together to address fundamental questions about many-body quantum matter, right? And one unifying thread driving this confluence is the application of information theoretic insights into modern many-body physics, right? So for example, studying the dynamics of quantum information or quantum entanglement, whether in systems of electrons and solids or cold atomic gases or black holes, has led to fundamental new insights which are key to understanding questions ranging from the black hole information paradox to foundational questions of quantum thermalization and many-body localization, to more practical attempts to build quantum simulators or quantum devices in the laboratory. So indeed, we're really coming into this culmination of years of sustained and remarkable progress in the development of designer quantum simulators across a variety of platforms ranging from superconducting qubits to trapped ions. So these platforms give us a great deal of control, a great deal of simulability. You can really by now, by looking at this array of different devices, you can explore systems with varying Hilbert spaces in different dimensions with different types of interactions. So we really had this very rich playground of experimental platforms for realizing lots of different types of physics. Okay, And this really represents decades of effort across academia and industry, perhaps conceptually starting with Feynman's famous quote in the 80s, which said that nature isn't classical. And so if you want to make a simulation of nature, we better make it quantum mechanical, right? And indeed, as predicted by Feynman, this is not an easy problem. And there's always this trade-off, because large quantum devices are always threatened by environmental decoherence, right? So there's this constant trade-off between the size or number of qubits in the platform that you're trying to simulate and various sources of error that can mess with your simulation and destroy the coherence that is needed for this truly quantum calculation, right? So while it's also true that most efforts or many experimental efforts to build these simulators or devices are broadly motivated by the quest to build a fault-tolerant quantum computer, this is still extremely far into the future, right? So we need many, many millions of qubits with a very low error rate to truly achieve fault tolerance. But while this ultimate goal is very far into the future, the possibility of harnessing the computational power of the quantum world with noisy intermediate scale quantum devices is already a reality. Okay, so this noisy intermediate scale quantum or NISQ devices, this is a term coined by Preskill. And when I'm talking about NISQ devices, I mean, you know, systems with 10 to 100 qubits and maybe 1% error rate in their fidelities. Okay. So a notable milestone in this context, which I'm sure all of you are aware of, was Google's recent announcement of quantum supremacy in their Sycamore device, which is a Josephson junction-based platform with 53 qubits, okay? So to demonstrate quantum supremacy, Google selected a very abstract information theoretic task, which was to simulate the output of random circuits, okay? So this is just a sketch from their paper of what their platform looks like. Okay, so each of these, so they have a series of qubits which are represented by the crosses. This is in a 2D array, and then they can have gates or that they can apply between these qubits with couplers. Okay, so time would go up in this direction if they keep applying different gates in time. Okay, and they had this very abstract task, which was, you know, you start with some initial state that's easily prepared. You run this quantum circuit on that state, and then you sample from the output distribution of this circuit, okay? So quantum mechanically, they just run the circuit many times and sample from that distribution. But classically, this is a very hard task, which would grows with the exponentially with the number of qubits and takes a very, very long time, okay? So they worked hard to benchmark that their quantum computer was working correctly. And, you know, while they selected this pretty abstract information theoretic task, which doesn't really have any obvious applications in and of itself, although there are a few proposals for what you might do with this, their announcement did signal in a very clear way that after years of effort to design platforms for, you know, individual circuit elements, like, you know, can we benchmark and really test the functionality of a single qubit or a single gate in small scale proof of principle experiments, we're now at the point where, you know, all of these can be deployed together to address real scientific problems on some intermediate to large scale, okay? So there are many research efforts that are now focused on applications for these NISQ devices, ranging from quantum chemistry simulations to optimization algorithms. However, you know, the perspective that I want to take in this talk is that a quantum computer is also necessarily a highly controllable many-body system with a sizable Hilbert space, right? And so these advances are also extremely tantalizing to many-body physicists. These devices bring new capabilities. So it's natural to ask, what new kind of physics can they host and discover when viewed as experimental platforms in their own right, okay? So this talk is motivated broadly by asking, what does the NISQ era of tunable, programmable quantum systems portend for many-body physics? And in particular, which physical phenomena in the realm of quantum statistical mechanics can these devices realize that have either not been or cannot be as crisply demonstrated in any other more conventional setting? Okay, so by conventional setting, I'm thinking of solid state materials, or I'm even thinking now of analog AMO simulators, which have been studied for a long time now, okay? And So this is the broad motivation. Narrowly, I want to ask, what interesting physics can be realized immediately with Google's Sycamore device? Okay, so we're going to take a particular one of these NISQ devices and ask immediately, if I'm viewing this as a many-body physicist, what can I do with it? Okay, so there is an immediate kind of conceptual challenge with this program that presents itself, which is that as condensed matter physicists or many-body physicists, we're usually used to studying time-independent Hamiltonians, okay, whether it's the Ising model, Heisenberg model, your Hubbard model, whichever your favorite time-independent Hamiltonian is, right? And in these time-independent Hamiltonians, we typically look for new kinds of universal emergent phenomena in equilibrium Gibbs states, or in low temperature states, or in ground states, okay? So usually you have in mind some gapped time-independent Hamiltonian, and you go in and you look for phases and phase transitions by studying the properties of correlation functions, or by looking at the topological properties of ground states or equilibrium states, okay? And then we usually say that, okay, all Hamiltonians that can be deformed into each other in some parameter space without closing a gap belong to the same phase. These phases have universal properties, phase transitions have universal properties, right? And while we expect there to be interesting quantum order and phase structure at low temperatures, right, the high temperature regime is usually thought to be thermal, classical, boring, okay? So we're usually studying these low temperature phases of gapped many-body Hamiltonians in condensed matter physics, right? On the other hand, the natural evolutions that are implemented in gate-based devices such as Sycamore are quantum circuits rather than Hamiltonians, okay? So in this view, we're thinking of quantum mechanics much more generally, right? So before you started doing condensed matter physics, if you were just studying quantum mechanics in a textbook, what you learned about is that quantum mechanics is defined by unitary evolution very generally, perhaps interrupted by measurements, right? And indeed, in these gate-based platforms, it's very natural to think of a very general unitary evolution that's implemented by unitary gates, perhaps interrupted by measurements at various times, okay? There's no real time-independent Hamiltonian that you need to think about, right? And the evolution is from general initial states that are not low energy that are not low energy in any useful sense, okay? So I want to emphasize here, so we want to think about many body physics in this paradigm of unitary circuits, rather than the usual way in which we're used to thinking about many body physics, which is as a function of time-independent Hamiltonians, right? And there's another trade-off here, which is that when these devices require a high degree of unitary control, right? But there's a trade-off between unitary control and platform size, so that again we're naturally going to get some variation in the individual circuit elements, right? So it's going to be very hard to arrange a circuit to be exactly the particular gate that you're looking for, okay? So this again presents a challenge in simulating a very fine-tuned model system, okay? So not only are we thinking about time-independent Hamiltonians, but we're thinking about unitary circuits with some inherent randomness in some sense, okay? So the question would be what universal, how do I think of unitary circuits or quantum circuits are very common tools in quantum information theory or quantum computer science, but they're a pretty different playground for a many body physicist, right? So if I want to think of ideas of emergence and universality, how do I do that in this setting of unitary circuits? Okay, so that's going to be the subject of the talk. And I want to emphasize here that I'm not thinking about quantum devices as universal quantum computers, okay? Because as a universal quantum computer, once you have a universal gate set, which is, and the system is of a sufficient size with sufficient fault tolerance, you can use this gate-based architecture to simulate whatever you want, okay? That's what a universal quantum computer is. So you can use a platform of this kind and solve the Hubbard model if you wanted to, okay? But that's very, very far in the future. So I am not thinking of these as universal quantum simulators, but instead I am interested in the physics that these platforms can immediately and naturally realize versus physics that they can universally and asymptotically realize far into the future, okay? So that's the program. And the good news is that starting with different initial states and doing time evolution is precisely the domain of non-equilibrium quantum mechanics. Okay, so we can actually rely on a parallel set of developments in quantum statistical mechanics, which furnishes a domain where the specific challenges that I just outlined turn into strengths. Okay, and one specific development that I'll use in this talk is the assignation of robust phase structure to many body systems out of equilibrium. Okay, so I can think of many body quantum systems out of equilibrium in many different ways. Specifically in this talk, I'll have in mind either periodically driven or periodically driven systems, which are known as Floquet systems. Okay, so this is again not a time-independent Hamiltonian, or I'll have in mind systems that are many body localized. Okay, so these are systems which I'm not going to have time to give you an introduction to many body localization, but what you should know for the purposes of the talk is that localized systems are usually disordered systems that never reach thermal equilibrium. Okay, so most of our, the foundation of quantum statistical mechanics is that you prepare some system, you can prepare it in some out of equilibrium state, and if you wait long enough, the system approaches some general equilibrium state, and then you can play your game of computing order parameters and correlation functions in these equilibrium states. But in a localized system, you can start with some very, very special non-generic initial state, and some local memory of that initial state will persist forever. Okay, so the system never reaches equilibrium. And the remarkable realization over the last few years is that even though equilibrium thermodynamics and this whole foundation that many body theory rests on goes out the window when thinking about these systems, the notion of phases of matter and phase structure need not. Okay, so you can still crisply define a notion of phase structure in systems, in many body localized systems that are out of equilibrium. And in particular, you can get new kinds of phases of matter that may be disallowed in equilibrium due to the strictures of equilibrium thermodynamics. Okay, so here I have a very cartoon picture where I'm just tuning some parameter, I'm tuning some interaction strength, and maybe once my interactions are large enough, my system is thermalizing. Okay, and what I want to show here is that just as there are many different kinds of thermalizing phases that you know, there are also many different kinds of MBL phases. Okay, MBL is many body localization. So you can have an MBL paramagnet or an MBL spin glass, right? And these are phases that are dynamical phases. Okay, so these are characterized by sharp signatures and in the dynamical properties of the system, but these phases and phase transitions are invisible to thermodynamic quantities. So you can look at a Gibbs state, and the Gibbs state may show no signatures of these phases, but that's okay because the Gibbs state is not meaningful in a system that doesn't reach thermal equilibrium. Okay, so for this talk, what I'm going to do is present to you a specific proposal where we plan to use Google's Sycamore device to realize what's known as a many-body localized time crystal, which is a specific non-equilibrium phase of matter with a unique pattern of spatiotemporal order. And this is a phase of matter that is provably disallowed in an equilibrium setting, but actually finds a new life in this out of equilibrium context. Okay, so the outline of the talk is that I'm going to review the time crystal phase. I'll give you a summary of various experiments that have been performed to see this phase. Okay, some of you have no doubt seen headlines that have claimed to realize time crystals in various experimental platforms. So you may be wondering, why do I need Google Sycamore device, or why do I need this NISQ platform to see this phenomena? Actually, it turns out that a closer analysis of all the experiments that have been done on time crystals so far reveals that a genuine realization of this phase, or actually for that matter, any non-equilibrium phase of matter, has proved elusive for different reasons in each of the experimental platforms in which it is being explored. Okay, so there are fundamental definitional aspects of the physics of this phase that have not yet been observed. Okay. However, these experimental platforms have taken us a long way into actually being able to identify what the desired experimental capabilities are, right? So we're not shooting in the dark here. These experiments made a huge amount of progress in seeing precursors of this phase, and then from those precursors, we were able to identify, these are the ingredients that a pristine incarnation would have, and this is what we need to get there. Okay, and with those experimental capabilities identified, we can now do this really cool thing where we can, look at the Sycamore device. We can see all the different capabilities it offers us in terms of the gate set and the capabilities of preparing initial states, the capabilities of control, the capabilities of measurement. And we find that all of this really is almost tailor-made to realize this phase. Okay, so then I'll tell you about how you can take this phase of matter and actually realize it on Google Sycamore device, and what the signatures and model would look like. Okay, so that's the broad program. Maybe I'll stop briefly for questions here before moving on, if there are any.
Do you have any questions?
Okay, I'll stop once more in the middle of the talk, so if there's nothing yet, I can go on. Okay.
Actually, I have one question. So you have mentioned that you separate your systems that can be characterized by the Hamiltonian and by
sorry, Dimitri, you've cut off.
the unitary evolution. So it's something similar to the Floquet phases that are described by the evolution operator. Do you hear me?
No. Sorry, your voice was just coming and going. Can you repeat the question, please?
The question is, so you have separated systems into classes, that one is characterized by the Hamiltonian. The second is that some by unitary shifts. So you need to classify the unitary operator of the system.
Yes.
Am I right? It is similar to the Floquet phases that are characterized by the.
That's right, but the Floquet phases make it a little bit easier because at least you have a single unitary operator that then gets repeated in time, and that's what I'll be focusing on. But in general, your time evolutions can be even more general, right? So you can just have a unitary which is not periodic in time, and then you'll be looking at the steady states of particular unitary evolutions characterized by some stochastic parameters, and see if you can define some phases in that manner. So that's an even more challenging program. But for now, we'll stick to Floquet unitaries. Yeah.
Okay, thank you.
Yeah. Okay, good. So to start, let's start with the question of what is a time crystal, right? So a time crystal is a phase of matter that spontaneously breaks time translation symmetry. Okay, so your laws of nature are invariant under spatial translations and time translations, and just like a system that spontaneously breaks spatial symmetry is known as a spatial crystal, a system that spontaneously breaks time translation is known as a time crystal. Okay, so what this would mean is that even though the rules underlying the system are time independent, the state of the system displays some sort of periodicity in time. Okay, so naively, this seems really simple. It's just another symmetry breaking. But actually defining this turns out to be a really subtle business. There's lots of possible loopholes that present themselves, and we actually spent a lot of time trying to sort this out, and I direct you to this review that we posted last year for what some of these issues might look like. Okay, but one key thing to keep in mind when defining such a system is that when defining a time crystal is that we must consider macroscopic many body systems. Okay, so few body systems routinely and regularly break time translation symmetry and exhibit recurrences or revivals, right? So simple example is if you just have a Rabi oscillator or a single spin in a magnetic field, it's going to show some oscillations. Okay, so that's not a big deal. So even if you have a few body system, to break time translation symmetry, you don't necessarily need periodicity in time. You can have, you just need to have some time dependence, right? So if you have a few body systems, such a system is always going to show you recurrences and revivals, like Poincare recurrences. So if you have only one or a few levels in your Hilbert space, time translation symmetry breaking is the norm, okay? There's nothing special about it, okay? But by the time you think about a macroscopic many-body system of many particles all interacting strongly with each other, and you're looking for some spontaneous pulsing of the system without any outside source of energy, okay? This now starts looking perilously close to a perpetual motion machine, okay? So the notion of time translation symmetry breaking is only non-trivial in this setting of a large many-body system. And in this setting, if you think carefully about how to define this system, you can show, and you can in fact provably show that this kind of time translation symmetry breaking is forbidden in the thermal equilibrium states or ground states of many body systems. Okay, so there's a variety of results that show this, and intuitively you can understand this as, if you have a many body system, this is a very intuitive picture, but indeed, if the many body system reaches equilibrium, the equilibrium state is characterized by a lack of time dependence, right? So searching for time dependence in the equilibrium state already shows you why this would be challenging. Okay, so that's what we're looking for. We're looking for this kind of macroscopic spontaneous clock. And if we're working in the context of time-independent Hamiltonians and their equilibrium states, you can probably show that you cannot get this kind of clock, okay? So instead, we're going to consider Floquet or discrete time crystals, okay? So now I'm not going to be thinking of systems that are time-independent, but I'm going to be thinking of systems that have a periodic dependence in time. So
Apologies, everybody. We seem to have lost our speaker. Dimitri, are you still there?
Yeah, I'm here, but I don't see Vedika in the list of panelists. So it's probably her connection problem.
If everybody would like to take this moment to go and grab a coffee, hopefully we'll have Vedika back in 5 minutes. Dimitri, you could give us a song or something.
Next time.
Pressure.
I guess so, yeah.
Yeah.
Okay. Sorry, 1 second. Okay, is that, am I back?
Yep, that's perfect, Vedika.
Okay. Where did I get cut off?
Probably the next slide or few more.
Okay, all right. no, it's not letting me change slides. There, okay, good.
Yeah.
All right, good. So, right, so what I was saying is that we're considering periodically driven or Floquet systems. And in these Floquet systems, we don't have continuous time translation symmetry, but discrete time translation symmetry by integer multiples of the driving period. So so that's the intrinsic time evolution in the system. So if you want to break that time translation symmetry, then your observables have to show a time dependence that's different from just periodicity with period t. Okay, so in particular, something that would work, it's not the only option, is if your observables show period doubling. Okay, so if your system itself has a period t, but your observables respond with period 2t, then that's one way of getting
Sorry, Vedika, your sound is dropping out there. You might just need to repeat that bit.
This time. So an be that if can you hear me?
Not very good, actually.
For some degree of robustness over a range of parameters, because you don't want any fine-tuned points in parameter space. Okay, and actually, what happens in a many-body in a periodically driven system is that if you have a many-body localized periodically driven system, then there are no symmetries in the problem, and so the natural equilibrium state of a driven system is that it tends to heat up to infinite temperature. Okay, so it just keeps absorbing energy from the drive, and as a result of this absorption, it just heats to this featureless infinite temperature state, which can't show you any kind of non-trivial order. Okay, so in order to avoid this heat death, you really need some notion of localization, and that's where many-body localization would come in. Okay, and this is all I'm going to say about MBL, that we need it to avoid heating to infinite temperature. And there are various results which tell us that if you have a periodically driven Floquet system, which is disordered and weakly driven in an appropriate sense, then you can get it to be many-body localized. Okay, and what we'll be looking for as a hallmark of this phase is spatiotemporal order, which is long-range order in space coupled with period doubling in time. Okay, so this is really this many-body phase of matter. So it's not enough to just see period doubling in time. You're also going to get this correlated long-range spatial order. Okay. So that's going to be the characteristics. We're going to look for period doubling. We're going to look for a robust phase of matter. It's going to be many-body localized to avoid heating. So this robust period doubling lasts forever. And we're going to look for spatiotemporal order. Okay. So I should say here that, when people hear period doubling, they think that, oh, again, this has been known forever because there's nominally similar period doubling behavior across a range of familiar systems, from parametric oscillators to Faraday waves. Okay, but in all of these systems, they're all kind of one or few or effectively few body systems in a particular sense. Okay, so they're not, whereas what we're talking about are genuine many body phases of matter in an isolated quantum system, and this requires us to think about Floquet many body localization. Okay, so why are we proposing to realize this DTC in Sycamore? Okay, one, because it's a highly non-trivial, non-equilibrium many-body phase of matter. Okay, so this was very surprising that it even exists, because of its proximity to perpetual motion machines, it has this form of cool spatiotemporal order. Okay, so it's this new kind of phase of matter that, and it hasn't been achieved yet in any experiment. Okay, so this would be something new that this platform can do. Okay. The other thing is that if you have a Floquet system, thinking of it as a quantum circuit is actually rather natural. Okay, so you don't have to. So the natural realization is that of a circuit rather than a time-independent Hamiltonian. Okay, there are signatures of this phase in the dynamics rather than diagnostics and equilibrium thermodynamics. Okay, so if these circuits are operating in the mode of preparing an initial state and then time evolving it and then searching for some dynamical signatures, those are rather natural. Okay, and those are the prime signatures of this phases. And then disorder, say due to variations in the circuit elements, that's not only tolerated, but actually essential for stabilizing many-body localization. Okay, so this notion of having a random circuit, right, that you can control in some way is actually, and look at time evolutions from generic random initial states is very naturally tailor-made to the kind of physics that we're looking for when we're searching for non-equilibrium phases of matter. Okay, so I want to briefly just describe a model system in which we can see this kind of physics. Okay, so we'll be looking at a periodically driven Ising chain. Okay, so I have in mind here, and we're going to come to a circuit realization of it, but for now, let me just think of a global time-independent Hamiltonian. Okay, so I have a Hamiltonian. It's going to toggle between two parts. Okay, so in the first part of the period, I'm acting with a Hamiltonian that's kind of aligned along the x basis. Okay, so that's what I'm calling hx. And in the second part, I'm acting with something that's more in the z basis. I'm calling that hz. There's a particular version of this that's exactly solvable, and because it can be mapped to free fermions, and that's if you pick the hz to just be a nearest neighbor Ising coupling in one dimension, and the hx to just be a global Ising field. Okay, so I'm acting with some Ising couplings for the first part of the drive, and then I'm acting with some global field in the x direction, but actually enacts a rotation of spins in the z basis about the x-axis. Okay, and then over multiple periods, I just see this repetition where I'm going to go from acting with hz to hx, hz to hx. Okay, so that's what I'm going to do. This particular phase, this particular drive actually has 4 different phases. Okay, so there's 2 of these phases are phases that can exist in an undriven system, but 2 phases are genuinely new to the driven localized setting. One of these is a Floquet symmetry protected topological phase in SPT. And the other is what we call the pi spin glass, or this discrete time crystal phase, which is generally new to the driven setting. Okay. So to give you a very quick intuition for what this phase is doing, it's easy it's useful to study this model in a particular limit. Okay, so let's consider the case where I have my hz, right, and the hz is again just some Ising coupling. I'll usually be considering disordered Ising coupling, so there's some randomness in these jij's, but then the hx is tuned so that the parameter here, which is pi over 2, is tuned to enact a perfect pi rotation. Okay, so if you have this global field, right, you're enacting rotations about the x-axis by 2 times g. So if g is set to be pi over 2, you take all your spins in the z basis and you perfectly flip them. Okay, so at exactly this value in parameter space, I start with some string of spins. Okay, so some pattern of ups and down spins. Okay, they pick up some phase under evolution with hz, and then when I act with hx, all the spins get exactly flipped. Okay, and then I do it again and again. So you can see here trivially that every 2 the spins get flipped, and then they come back, and then they get flipped, and they come back. So the state of the system only comes back to itself every 2 periods, even though the periodicity in the Hamiltonian is t. Okay, so that's the period doubling. And what you can do is that, the way we characterize phases and phase transitions formally is by looking at the eigenstates of this Floquet unitary operator. And if you look into individual eigenstates of this unitary operator, you'll find that they're characterized by a glassy pattern of long-range spatial order. Okay, so you have some, if you measure some long-range correlation function of your Ising spins, there'll be long-range orders. So this is the spatiotemporal order that we're after, which is this period doubling in time and long-range order in space. And even though this long-range spatial order, you don't have access to individual many-body eigenstates in this system. These two quantities together have sharp signatures in dynamics of the problem. Okay, so these are sharp signatures that you can probe in dynamics, and you don't have to rely on looking at individual eigenstates. Okay. So good. So far, this is rather trivial. I'm just telling you that I'm coming in and exactly flipping spins every period. So it's no big deal that it comes back to itself only after 2 periods. Okay. So the non-triviality comes from the fact that in order to define a robust phase of matter with spatiotemporal order, I need to be thinking of ways in which I can perturb the system while still retaining this signature. Okay, so while still retaining the signature spatiotemporal order. So indeed, what you can show is that there, no matter which way this phase actually, it's topological in a sense, because it forms this example of an absolutely stable phase of matter, because I can perturb it weakly in almost any way that you can think of, right? And the signature phase persists, okay? And that's not true of all of these different phases. It's only true of this pi spin glass time crystal phase, okay? So what are some ways in which you might perturb it? Okay, so a very intuitive one is to enact an imperfect rotation, okay? So instead of flipping your spins exactly by pi, let's say you flip them by pi minus epsilon, okay? So that's going along this axis in the phase diagram. Okay, so that's like if you just had a semi-classical picture in mind, you would think that you had a spin pointing up, then you try flipping it, and instead of flipping it completely, you flip it by pi minus epsilon, and then you do it again, and then you do it again, and then it accumulates this error in time, right? Because you're not coming back to period doubling. Okay, so that would be the semi-classical picture. But instead, we find that for a finite range of imperfect rotation angles, the response remains exactly locked to period doubling. Okay, and this locking is really coming from this intrinsic long-range spatial order. Okay, so you have this like giant super spin, if you will, because of this long-range spatial order, and that's collectively being locked at period doubling, even when you make this finite error in the rotations. Okay, so that's one thing you can do. The other thing you can do is to add all sorts of perturbations to your Ising interaction. So you can add in, you can add in Ising symmetry respecting perturbations like XX and YY terms. You can add in, you can even add in Ising symmetry breaking fields. Okay, so this is again really important, because usually if you're thinking of a ferromagnet or a spin glass, okay, so in the ferromagnet you have, it intrinsically relies on the Ising symmetry, okay? So you have a spontaneous symmetry breaking between some all up state and an all down state, okay? But that distinction is not meaningful if you didn't have the Ising symmetry to begin with, okay? For this phase, you can actually explicitly break the Ising symmetry by acting with fields, but that does not destroy the signature of the phase, okay? So that's what this figure is trying to show, that you can act with whatever interactions you want, and this pi spin glass time crystal phase persists despite these perturbations, while all the other phases just look paramagnetic. Okay, so now we have this robust phase of matter with spatiotemporal order, where I'm allowed to have all sorts of interactions. Okay, I'm not fine-tuned in any way, as long as they're dominantly Ising interactions during this first part of the period, and then I can enact imperfect rotations in the second part of the period. Okay, so this combination of stability and visible experimental signatures, led to a lot of excitement. So almost immediately after the theoretical proposals, there were a series of experiments that try to see this phase. And what's really remarkable is how much progress could be made on the experimental side in a very short period of time. Okay, so there were very different platforms that tried to see this, and they actually all saw, despite their differences, they all saw very similar kind of universal signatures of this phase. Okay, so the 3 different platforms where this has been seen are disordered nitrogen vacancy centers in diamonds. So there's 1 million or so qubits here, effective qubits. Okay, so there's a very very dense system. It's got long-range dipolar interactions. Okay, so it's a very messy system where you don't really have individual control over your qubits. Okay, then there is another system which is a system of trapped ions in one dimension. Here there's only 10 trapped ions. Okay, and you have a great deal of control over every single ion. And there's particular kinds of disorder that you can arrange, but again, this is a long-range interacting system. And the third platform in which it was seen was an ordered NMR 3D crystal. Okay, so this is just a spatial crystal with no disorder. It's an actual regular spatial crystal in 3 dimensions. And again, this was looking at 1 million or so effective qubits. Okay, and this is very far from any system that we have in mind when we're thinking about many-body localization, because there's no disorder, there's long-range interactions. And in all these 3 platforms, they did a very similar drive where they started with dominantly Ising interactions, and then they enacted some kind of imperfect rotation. Okay, and as a result, and in doing this protocol, they prepared some initial state which had some polarization, and they measured this polarization in time every Floquet period. And what they found was that this polarization is actually oscillating. It's going from net up to net down, and it's oscillating in time. Okay, so it's showing this kind of period doubling behavior, which in frequency space corresponds to this subharmonic peak at half the frequency. Okay, so these experiments all showed very similar behavior, but it was very surprising because actually most of these were not expected to be localized, and especially this NMR crystal was not expected to be localized at all. So it was a mystery as to why they were all seeing this behavior. Okay, and in studying them and understanding them, we now have a lot of understanding about what's going on in each of these different platforms. And what we know is that this diamond experiment is forming what's known as a critical time crystal. Okay, so these are systems in which the system is eventually thermalizing, but it's doing so in a very slow power law fashion. Okay, so even though if you could wait infinitely long, your system would destroy all its signatures of time crystal behavior, it's doing so very slowly. So if your experiment only has access to a finite time window, within that time window, you can kind of see this period doubling behavior. Okay. The other 2 experiments, this trapped ion experiment, they were in 1D. They had a lot of control. They could engineer a lot of disorder, and this was really designed to be as close to MBL as possible. But actually, a closer analysis of this experiment also shows that the effective disorder that they were able to engineer is not enough for getting this kind of stable MBL time crystal phase, because this effective disorder kind of echoes out over 2 periods. I'll explain that in a second. Okay, so this actually forms an example of what's known as a pre-thermal time crystal. And this pre-thermal time crystal is a time crystal where you can again see signatures of time crystal in order for a long period of time, but eventually the system, this signal goes away. Okay, the way pre-thermalization works is that your system looks like for a long time it's governed by some kind of effective Hamiltonian, okay, in an appropriate rotating basis. So one hallmark signature of pre-thermalization is a strong initial state dependence, because what happens is that states which are low temperature with respect to this effective Hamiltonian can show a long-lived signal. That's what this tiny little figure, which I don't expect you to be able to read, but I've just put it here as a cartoon. That's what this is showing, that specific initial states can show a long-lived signature. Those are states that are low temperature with respect to this effective Hamiltonian. On the other hand, other initial states, which are high temperature with respect to this effective Hamiltonian, can decay very, very fast, okay? If you had a genuine bona fide MBL time crystal, there would not be this strong initial state dependence, okay? So this experiment happens to be a pre-thermal time crystal, and the 3D NMR crystal, that was even more surprising, because not only was it not MBL and not disordered, it actually wasn't even pre-thermal in the usual sense, because for usual pre-thermalization, again, you want to be at low temperature with respect to some effective Hamiltonian, but NMR systems always operate at very, very high temperatures, okay? So this pre-thermalization is not possible for this very high temperature initial state, which is well above any kind of ordering temperature that you might imagine, okay? So this turned out to be a new type of pre-thermalization that we were able to formulate, which is a type of, it sounds oxymoronic, it's like pre-thermalization at infinite temperature. So you can have infinite temperature systems that nevertheless look pre-thermal if you end up getting some additional kind of emergent symmetry. In this case, this was a U1 symmetry. And if you prepare initial states that couple to this symmetry, okay? So these experiments, they were beautiful. They were really experimental tour de forces. They taught us a lot about, what are the different kinds of phenomena that we can get that is not a time crystal, but they were not a bona fide time crystal phase, okay? What they did do is they allowed us to pinpoint what are the desired experimental capabilities that we need, okay, in order to see this physics. And what we need is for our system to be large enough and generic enough to probe many body physics. Okay, so this was the first thing that I was telling you about, because if it's not, few body time crystals are not special. Okay, we need the coherence time of the system to be long enough that you actually probe a dynamical phase of matter. Okay, because the dynamical phase of matter is defined by the asymptotic properties of the system. So you can't look at any short time transients, and you need to be able to distinguish the asymptotic dynamics that you're looking for from short time transients. Okay. And then we need various results. We need various capabilities for stabilizing MBL. Okay. And this is important for heating this, for preventing the system to heat up. So in particular, we need short range interactions. Long range interactions are known to be incompatible with MBL. A lot of these systems have dipolar interactions, which fall off as 1 over r cubed in 3D. So those are not enough for MBL. And then we also need disorder in the Ising even couplings. Okay, so this is subtle. I won't have time to go into the details of why this is, but if you only have disorder in the fields, then your disorder effectively echoes out over 2 periods, and that's not enough. And this was actually the main problem with the trapped ion setup, because they could only engineer disorder in these Ising fields and not in the couplings, okay? So finally, so this is, these are the features, these first 4 features are what you need for realizing this kind of physics. And the very last 2, okay, is for measuring and distinguishing asymptotic time crystals from their pre-thermal variants, okay? So you could wonder that, okay, you have a pre-thermal time crystal. This shows you the signature that you want for some finite amount of time. If your experiment itself only has access to a finite amount of time, then how do you use an experiment that lasts for a finite amount of time to distinguish and be able to tell you whether the system is a genuine pre-thermal time, is a genuine asymptotic time crystal or a pre-thermal one, right? With access only to finite time information. And some things that you can do is to look at site resolved observables and different initial states. Okay, so these are probes which even in finite time experiments can distinguish between pre-thermal and non-pre-thermal time crystals. Okay, because if you vary different initial states, an MBL time crystal should show you the same signatures regardless of which initial state you look at. Whereas pre-thermal time crystals will only show you the signature with some initial states that are effectively low temperature or low entropy with respect to some emergent Hamiltonian or emergent symmetry. And secondly, you want to be able to look at site resolved observables rather than global polarizations, okay? So again, for an MBL system, a site resolved observable will show you period doubling, whereas for something global, like if you just had a global U1 symmetry, then your signal can get confused because even a global magnetization measurement could show you period doubling, but that's just coming from an overall symmetry rather than many body localization, okay? So to put it all together, we have various requirements divided into roughly 3 categories. There's definitional, requirements that we need for defining a time crystal or any dynamical phase of matter, which is you want many body systems and long coherence times. You need to stabilize MBL, which requires short range interactions and Ising even disorder. And you need to be able to detect your time crystal phase, which requires site resolved measurements and varied initial states, okay? And then you can go through the list of the different experiments that have been done so far, and you can see that, all of them have one or more of these ingredients lacking, but each of these was instrumental in allowing us to make this list of ingredients that we needed, okay? So once we do this, we can actually look at Sycamore and we find that it checks every one of these boxes and seems tailor-made for this application, okay? So now I'll briefly describe that in the rest of this talk. Good, so how do we realize a time crystal on Sycamore? Okay, so this Google device has a natural gate set. Okay, it has a gate set which is this transmon gate, which is G, and this transmon gate, they have effective qubits built out of these Josephson junctions and superconducting elements. So this transmon gate G is parameterized by a variable theta and a variable phi, and it has this Ising type interaction that we need, along with this XX and YY perturbation, but that's okay because we know this time crystal is stable, so we can perturb it in this way. The theta and phi are tunable parameters, okay? And in particular, because we want this to have disorder in the Ising couplings, we can put disorder in each of the phis in each of these different gates, okay? So we can make this very disordered, and we can make the phi large compared to the theta, so it looks dominantly Ising. So we have tunability over all these different parameters here, okay? So those are my gates, and then I can add in on-site Ising fields. Those are these RZs, okay? These just add more randomness to the problem. They make the problem interacting. So this can optionally be present or not present. It's not necessary, okay? And then they have these single side gates which enact rotations about the x-axis, and these can allow rotations by any angle, okay? So there is this imperfect rotation that we need, and these dominantly Ising interactions, and they just exist naturally from the gate set that you have in Sycamore. And because the theory of MBL in this phase is best understood in one dimension, you can actually take the 2D chip, right, and these gates and these qubits, and you can act with these gates in this 1D way by snaking through this chip. Okay, it's interesting to also think about 2D non-equilibrium phases of matter. That's something we're thinking about, but for now, even in 1D, you can snake through this device this way and realize this effective 1D system. Okay, based on these parameters, we can get an effective phase diagram for this system. Okay, so the two parameters I'm plotting here are G. The G is controlling the angle of rotation. Okay, so when this rotation is exactly pi over 2, you're doing this exact pi flip, and then you see that you can do this rotation for some finite deviation from that, and you continue to get this MBL time crystal phase. When you have almost no rotation, then you have an MBL paramagnet, and everywhere in the middle you have this thermal phase. Okay. And the other parameter I'm plotting on the y-axis is theta bar, which is the addition of this xx plus yy term, which takes you away from being dominantly Ising. Okay, so your Ising interactions are drawn from some disordered distribution, and then you can perturb away from that solvable limit by adding both theta and g, and you can get this phase diagram that you can work out. Okay, you can understand various limits and fit, and you can work it out numerically. And then what we can look at are signatures of the time crystal on this device. So one thing that they can measure very easily is starting from a whole variety of different initial states. Okay, so a lot of the previous experiments had started with just nearly polarized states. Okay, so nearly polarized states are the worst at distinguishing between pre-thermal time crystals or U1 pre-thermal time crystals or general time crystals, but you can now start with any random pattern of sigma Z states that you want. These are still low entropy states, so we're still thinking of product states, but just think of some random pattern of Z spins. So you start with such a state, you look at it in time, and in the time crystal phase, this autocorrelator is just measuring sigma Z as a function of time. And you see this nice period doubling that these are numerical simulations. You see that it basically persists forever, right? It does persist forever in the numerics here. And in Fourier space, this looks like this subharmonic peak at pi rather than 2 pi, okay? In the thermal phase, because this is a Floquet system which heats up to infinite temperature, if you measure something similar, it very quickly decays to 0 and thermalizes. Okay, so this is the lack of any kind of, this is saying that all observables will thermalize to the infinite temperature value, which is just 0. Okay, and in a localized paramagnet, an MBL system is something which retains local memory of its initial conditions forever. So if you start with some sigma Z state, right? And you measure, if you measure this correlator in the paramagnet, then you see that it retains some memory of that initial state forever. Okay, so it's not oscillating back and forth, but it is retaining that memory forever, and this corresponds to a delta function at 0. Okay, so this is localized but not a time crystal. Okay. What's neat is that in this device, you can actually just see spatiotemporal snapshots, which would just very clearly show you that there's some long range glassy order in space. It's called glassy order because you know that if you have various domain walls, okay, and these domain walls are pinned, so you can have random patterns of sigma z's. Okay, so if you go in and you measure some zz correlation function, these domain walls are not fluctuating, so you don't get a non-zero correlator, but you can get either +1 or -1, so it looks like a glass. Okay, so indeed, if you look at this MBL time crystal, if you start with some random initial state, you know, this is a color plot, so that's +1 and -1. So this is 2 ups, 2 downs, 4 downs. You know, you start with this initial state. You find that this initial state persists in time. Okay, but then it keeps flipping every period. Okay, so this is just a spatial picture of what we mentioned earlier. So if you measure a spin-spin correlation function between 2 arbitrarily distant spins, that's not going to be 0. It's going to be something +1 or -1, and then this pattern repeats in time. In contrast, in the thermal phase, everything just very quickly goes to 0. Okay, there's no spatial correlations, there's no temporal behavior. Whereas in the paramagnet, whatever initial state you have just persists forever. Okay, so there's no, this memory of this initial state persists. There's no kind of doubling of any kind, and there's no relaxation. Okay, so you know, inspired by this information theoretic quantities that these systems probe, we can in fact look at a novel measure of this phase, which is we can think of some kind of Hamming distance. Okay, so what a Hamming distance between 2 bit strings is, if you have some pattern of 0s and 1s, which is characterizing some sigma z product state, the Hamming distance between that pattern and another pattern is, you know, how many spins did you have to flip to go from one to the other. Okay, so what you can do is you can, you know, this is something that Sycamore is actually very naturally tuned to being able to measure. Okay, they can just look at this. So indeed, if you have an MBL time crystal, if you start with a particular pattern and everything flips, okay, then the Hamming distance is the size of the system, okay, because all the spins flip, and then everything flips back. Okay, so this is a video of the Hamming distance as a function of you know, these are distributions of the Hamming distance and as a function of time. And when I play this, you see that at even times, this Hamming distance is peaked near 0 spin flips, and at odd times it's peaked near near, you know, all the spins being flipped. In the thermal phase, this just very quickly goes to half the spins being flipped, because if you reach a thermal state, then you know, the most probabilistically most likely outcome is that with reference to any initial state, half your spins are flipped. Okay, and then in the paramagnet, this remains where it is. Okay, the Hamming distance is peaked near 0 because the memory of that initial state persists. Okay, so there's various crisp diagnostics we can use to tell this apart. But the last thing I want to discuss with you is the effect of noise. Okay, so indeed, as I started this talk, I said that, you know, we're going to be thinking about noisy intermediate scale quantum systems. Sycamore is 53 qubits at the moment. This is already much larger than the trapped ion experiment, which was on 10 qubits, but it's orders of magnitude lower than these experiments on diamond and on the NMR crystal, where we did not have site resolved control, but those were, you know, millions of qubits. Okay, so this is like 50 qubits. They're pushing 100, you know, as we speak. But one of the other things that's very good about this platform is that while all quantum simulators have to contend with the effects of environmental decoherence, Sycamore has an edge in that the noise has been calibrated with great care in this platform. Okay, so this should make it easier in practice to disentangle the contributions from kind of external environmental decoherence, because they have very good benchmarks for what these error rates are, versus internal decoherence, which is just the system itself is acting as its own bath and thermalizing, and you know that itself can cause the signal to decay. Okay, So what happens in practice is that, we can assume various error models. Okay, it depends on what level of error modeling you want to do. The simplest is to assume what's known as a depolarizing error channel, and you can get a conservative estimate of the error rate as 1%. And if you do that and you look at the same signals that you had before, you see that, the signal gets damped with this exponential envelope. Okay, but the point, and in Fourier space, that causes this broadening. Okay, but the point is that we know what the error parameters are. Okay, and with improvements in this error, you can cause significant improvements in the lifetime of the signal. Okay, so this is particularly nice in an MBL system. Okay, because when Google ran its experiments for a random circuit, the fidelity was decaying with the size of the system. Okay, so if there was some error rate, the fidelity of what they wanted was going down, in time and system size exponentially. However, in an MBL system, when you're measuring local correlators, your signal actually doesn't care about the system size. Okay, so you can get it only cares about the error rate. Okay, and the data for different system sizes is more or less unchanged. Okay. So this is really nice, because it's very, it's plausible to expect that if you make a small error at some location in an MBL system, it'll only affect observables in a small vicinity rather than completely randomizing the output state. Okay, so this is great, because already with the existing error levels in the system, a coherent signal should be observable for hundreds of periods, which is comparable to what's being done in the other platforms. Okay. But we now have much more control over the noise and concerted efforts to improve this noise threshold. And even a 1 order of magnitude improvement in this noise threshold can extend the lifetime of this time crystal by a lot. Okay, so that's the story in a nutshell. But I want to, in the last minute, I just want to briefly give some outlooks that, this was just one example of this very broad space of doing many body physics with random unitary circuits. And there's all sorts of very interesting questions that we can ask. And, so far we're asking these questions theoretically, because a lot of them are pretty hard to measure, but we're in the era where, the platforms to see and probe this kind of physics are just coming online. Okay, so we can ask about the dynamics of quantum entanglement in these circuits. And we find that, there's lots of universal pictures that you can make for how quantum entanglement grows in random unitary circuits that can apply to chaotic systems more generally. We can ask about chaos and operator spreading and out of time ordered correlators in these systems. We can ask how we can start building in various levels of structure into the random circuits. Okay, so in some work that I did, we considered random circuits with a global conservation law, which would have dissipation. And we asked how hydrodynamics emerges under unitary time evolution, because something like diffusion is inherently dissipative, while unitary time evolution is conservative. So how does hydrodynamics emerge in a closed quantum system? People are now starting to talk about measurement-induced phase transitions. Okay, so they have random circuits which are not just unitary but hybrid. So you have unitary random circuits which are interspersed with random local measurements, and as a function of the measurement rate, you can actually drive a phase transition in the entanglement properties of the system. And this is again a new type of phase transition whose properties are under active study. Okay, very ambitiously, there's this group of people who are starting to think about quantum gravity in the lab. Okay, so random circuits can serve as models of black holes. They can be fast scramblers. Okay, so there are various proposals for making toy models of black holes in the lab, which again go through the physics of random circuits. Okay, so there's this very rich arena of very different kind of very different types of questions we can start asking with these systems. Okay, so to summarize, an immediate near-term application of a NISQ device that I told you about is as a platform for many body experiments is to observe the time crystal phase. But longer term, we can ask various questions. For instance, this experiment that Google did was using the output of random circuits to benchmark how quantum their device was, right? Like the quantumness of their device. And that was a very information theoretic benchmark. And we can ask, are there insights from many-body physics? Are there particular types of intrinsically quantum phases of matter that we can use for benchmarking how these devices are operating, whether they're actually operating in some quantum regime protected from decoherence in some effective sense, right? There's this huge class of interesting many-body problems with random circuits like entanglement dynamics, chaos, measurement phase transitions that I briefly alluded to. And more generally, this view of NISQ devices as experimental platforms, calls on us as many-body physicists to treat these setups with the same level of attention and, with the same level of modeling that's been devoted to other more traditional systems, whether that's in materials physics regarding the choice of chemical compound or its synthesis, or in cold atomic systems regarding the choice of atom or molecule or cooling and loss suppression techniques. So there's a lot of physics here from both the engineering and experimental details side to brand new ways of thinking about emergence in many body systems in this universe of random circuits. Okay, so that's where I want to leave off. Thank you, and sorry for all the technical problems.
Thank you a lot for the interesting talk. Do you have any questions? Actually, I have one or two. So in Ising model, it's the limit when the interactions is long range, so it's effective between many neighbors. The mean field theory becomes applicable.
Yeah. Exactly. Yeah.
If you go from your physics to this limit, can the mean field approaches be helpful?
Yeah, that's actually an excellent question, because that's again coming back to this issue of few body versus many body. Okay, so there are various all-to-all models or very long-range models in which people have seen time crystal-like physics. Okay, and we have to be careful there, because when you're thinking of these systems in the mean field limit, right, what you're doing is effectively getting out 1 degree of freedom in the problem, right? So if you have kind of 1 effective degree of freedom in the problem, and that shows you some kind of rotation or oscillation, then that's kind of not so special in some ways. Okay, so the question then becomes, as soon as you start taking the corrections to that problem into account and viewing it as a genuine many-body problem with all these corrections built in, can you continue to see those oscillations? So the mean field limit can be useful, but it also needs to be interpreted with care, because it can precisely drive you towards this few body limit that we want to steer away from. So when I'm talking about many body systems, they don't have to be, when I'm talking about few body systems, there's the obviously few body systems, which is you just have four atoms to begin with, or there are the effectively few body systems where even though you started with 1 million atoms, the way they interact makes it look like you have effectively only 1 degree of freedom.
Okay, thank you. Yeah. So I'm not sure that we have other questions, but people could email if they have any. Thank you for a very nice talk. We really enjoyed it.
Yeah, thank you for the invitation. Okay, thank you.
Yeah. So we don't hear anybody, so we only panelists could clap.
Okay, all right. Okay, thanks. Bye.
Have a nice day for everybody.